Good evening, everybody. This is 7:30, and let's get started. So we have three more lectures to go before the final exam. One is today's, which is part three of the cache memory, and then we'll have one more for as a part four of the cache memory. And after that, we'll discuss virtual memory. Virtual memory topic is little bigger but combined into one lecture. So you may need to find more time to spend on the virtual memory to understand it better. But the good part of this virtual memory is also taught in the operating system class and from the operating system perspective. So we'll discuss virtual memory from the hardware point of view, like what is needed in the hardware support and how the virtual memory is dealt within the hardware. That's the part we'll be studying here. Um, I believe more fun part is in the operating system classes. So in that way, it is not that bad actually. But just an caution that, as I told you, this might take more than one day for you to grasp the whole concept, though it is just one lecture. Questions so far? Anything on the cache memories? Any other topics? Is there anything on the discussion? Let me see. No, nothing on discussion. So this, if you have reviewed this cache memory 3, this lecture 21, this lecture is oriented towards resolving the issue of the write operation. So far we dealt with the read operation, we understand that, understand cache operation in terms of reading, like when we are reading some data from the memory, if it is not there, how do we pick that out from the main memory and so on and so forth. Excuse me. But here the problem becomes when you are writing into the memory. It is not directly going into the memory, but it is first going into the cache memory. That means essentially the block where we are writing the data, that blocks become not synchronous with what the content is in down the hierarchy level. And that is the whole problem we're trying to solve with this write operation. And this whole situation is dealt with like different policies depending on what type of applications you are running into. Write through is a simpler circuit, no read time impact, but apply it where there is less write, like system level market analysis actually gives you the a picture that if your program, your application is going to be more like read memory oriented application. So in that case, write through is probably the right answer because of its simplicity. But in the write back, it is, remember, it is a faster, though it has a little complex circuit, digital circuit, uh, but it is faster, especially if you are using that in the write through approach and you see your write buffer is stalled very often because you have a very high frequent write operation in your application space. It's probably a good idea to get back into the write back mode. But all this management is done using this memory management unit, which we tend to view as a separate part than the controller, the main controller, which process everything, implements pipeline, and etc. So if you view it in a separate component perspective, then when the memory management unit is taking care and dealing with all this synchronization of the memory, picking up the block, and replacing the block, etc., during that time, processor actually has chance to look into the other task in parallel. It doesn't need to be stalled, and that's what was exploited in the hardware threading concept. Okay, and sometimes you hear the term hyper threading in some of the Intel processor. They are practically your hardware threading, the same concept as the Sun Oracle came maybe 10 years back or something like that time frame in their Niagara processor of the Oracle Sun. That same concept is nothing but an hyper-threading concept, and that is possible that because this MMU or memory management unit is taking care of your low-level data transfer between this memory hierarchy, where processor doesn't need to be involved and can spend that time looking at the other processes and other instructions which could go through these execution cycles. So with that respect, maybe we can do a little problem here where we need to actually wait for processor need to wait. Let me share my screen with you. Okay. Now, so here is a problem. So your project 2 processor is modified to hook into a cache memory system. That is, the states are introduced to handle the cache miss. Remember, like we have two places where we need to access the memory. One is during the instruction fetch, and other is during the memory cycle. So these memories, this processor is hooked into the cache memory system and running on 1 gigahertz clock. Now this system is connected. This system is connected to a memory system with a separate instruction cache and data cache. So these are like two main points, that it is not one single cache, but we are differentiating data cache and instruction cache. So it has instruction cache and a data cache. And both this cache has same access time, 1 nanosecond, and penalty of 150 nanosecond. The miss rate for this cache is instruction cache is 5%, and the miss rate for the data cache is 10%. Now, assume these following code are being executed in this processor, okay, for 10,000 times. So we don't need to worry about the data and everything. For 10,000 times, this is the loop. It will carry on. And this program is need to run throughout 10,000 cycle. So what we need to do is compute the program execution time so far for this program in microsecond unit. So what is going on here, in order to hook into the cache, we have this 5 cycle, right? Each instruction will take 5 clock cycle in normal. IDRF, EXE, MEM, write back, and instruction bits, right? And this system is something like very top level is like this. Like this is your microprocessor, and here is your memory system, which includes the cache and everything. This is memory system, not just the memory device on board. It's the entire memory system. And view of the microprocessor is that it supplies the address and bidirectional data, and also it receives the signal weight. If it is wait, that means data is not sent back from the memory system. So with that respect, what we need to do is to add additional cycle into it, conditional, if wait equals 1. And if wait equals 0, then it goes from instruction fetch to instruction decode. And similarly for the mem, till wait is 1, it stays in the memory stage. And only if it turns down to 0, then it goes into the write back phase. So with these changes, just take 5 minutes yourself to solve this problem. And then we'll open up the breakout room for your group discussion and try to solve this problem in the group. The time starts now. Okay, I'm opening the breakout room for you to work in a team and to discuss the solution of this problem. Okay, our time is up. Let's see. Let's wait for a couple of seconds for everybody to come back. Yeah, I believe everyone came back. Anyone want to discuss the answer, or at least came to an answer? No volunteer?
I got 970 microseconds.
917?
Yeah, 70. Yeah.
So 900.7.
Uh, 970. Sorry.
Or 970. Uh,
Yeah.
yeah, more or less similar. Similar. Maybe some assumption is not matching with my assumption, but that doesn't mean you are wrong. So let's anyone else. So my calculation is more like 900.06 microsecond, but maybe some approximation and assumptions are there for that part. Any other answers to this problem? Final answers? Okay, let me show you what I did. Okay, so first thing first, right? I always approach this problem like as if there is no wait time, like this wait time is not there. Then how much time it will spend in this whole 5 cycle iteration for this program, right? Now to do that, we must first calculate how many instruction um, will be executed for this program. So we can count the instruction. This is 1, 2, 3, 4. This is 4, 5, 6, 7, 8, 9. And we have within this loop, we have what? 1, 2, 3, 4, 5, 6. 6 instruction. And given that this 6 instruction is executed 10,000 times, so we can say that total instruction $60,000, 6 into 10,000 plus extra these 3. Okay. Now, this one, our clock frequency given here is 1 gigahertz. That means our time period equal to 1 by 1 gigahertz, which is 1 nanosecond. Now, incidentally, this number is same as your cache access time, 1 nanosecond. That means we don't need to bother about any extra cycle to be spent on the instruction fetch. What I mean by that, let's say this was given as 4 nanosecond access time. In that case, all the memory access, let's say instruction fetch, this access, need to wait for 4 cycle of the processor. This is the microprocessor clock cycle, right? 4 nanosecond, clock cycle is 1 nanosecond. That means this is already 4 cycle inside that. After 4 cycle, it will be done, right? So we had to add that additional cycle, even if without the miss penalty and everything. Okay, but this problem is a bit simpler. We don't have this situation. We don't have this situation of mismatching clock cycles, so we are good here. So this is 1 nanosecond, everything is sync up. So that means if there is no miss at all, we are talking about total time no miss is 60,003 multiplied by 1 nanosecond and multiplied by 5, because it's the 5 cycle execution multiplied by 5, which comes about, accordingly my calculation, the 300, about this thing, 302 microsecond. Okay. Now the next part. Next part is, out of this 60,003 instruction fetch, 5% will cause the cache miss. But this is instruction fetch. We are talking about the instruction fetch now. That means we are talking about the instruction cache here. So that means my 60,003 instruction, 5% cache miss, and cache penalty is 150 nanosecond. That means my time for, let me just remove this guy. Okay. Okay. Now, time for iCache miss. What is that calculation? 60,003 multiplied by 15%, sorry, 5%, which is 0.05 multiplied by 150 nanosecond, which according to my calculation comes about 450.02 microsecond. And similar thing, we need to do compute for the data memory access. Now let's look at the program. Where are my data memory? Data memory access is these, store word, and we have one more here. So 10,001. So this will be within the loop, 10,000 time plus 1. So that means we are talking about data cache miss 10,001 multiplied by, it's a 15%, right? It is the cache miss of 10%, not 15%, 10%. So it is 0.1 multiplied by 150, which according to my calculation comes about 150.02 microsecond. That means my total time, the total, is 300.02 plus 450.02 plus 150.02 microsecond, which adds up to about 906.06 microsecond. Is there something different than what you guys calculated? No? Everyone agrees with this number? Then let's take 5-minute break. About 8:12, we'll be back. Okay, let's get started. 812. Please go to your canvas and see there is a pop quiz. Uh, I'm entering a poll. If you are ready to enter the passcode to the quiz, please press yes. At that point, everyone is ready. I will open up the passcode for you. 33 of 56. Forty-seven of 56. I'll wait a couple of more seconds before I open it up. 50 of 56. Okay, I'll share the passcode now in a poll. Let's see, password, launch. I think couple of seconds to go for most of you. Let's see, what is our statistics tonight? Why the stat is not loaded? Okay, average is 62% with my high score 92%. Not bad, not bad. Okay, I will open up this quiz result to you so that if there is any discrepancy or point loss, let me know if I need to fix it. Let me know over email. Any question? So I don't have anything else for tonight, and I believe today's project 3 due tonight. Make sure don't be late. For late, it's automatically deducted point, right? You know that. Even if you pass just a few seconds after 11:59, it will deduct. System will deduct point. So make sure you go and have it on time.
So you go,
You
Kevin.
go first.
Okay.
Yes.
Professor, I
Yeah.
had a question. For the project, what files are we supposed to submit? Like
For the
official.
project, okay, that's a good question. What is in your what is in the discussion description? Let me see. Assignments, project 3. So I'm looking at the project 3 description. Okay. What you need to submit. Okay, so basically, remember we have this package, project3.zip, and under that package, you need to edit main the source file, and possibly you have added some test bench, which I don't test, which I don't use usually, but you can include that as well. But mainly your source code change that you have done for that specific files, like the one we have uh, asked in the lab and asked in that as a comment section for the projects. We only pick up those specific file and insert into our tester for tester implementation. So your test code, that zip file, should contain at least those file. I would suggest just zip up everything, your project directory, and zip up everything, upload. We just pick it up from that, whatever file we need. And definitely the report is a separate submission. Don't just put it a part of the zip file. Just make it a separate submission so that we can, the Turny team can actually verify your similarity score, and we can analyze based on that. Is that clear?
Yeah. Okay. Thank you, Professor.
Anything else?
I had a question about
Yes.
a mux in register file. You have it so that like if you read is 0, the mux should give high Z.
Right.
But the way like the wiring works, like it can only give an X value. Because if you put a high Z into a mux, like it goes through an OR gate or an AND gates, and that gives a 0. I mean, that gives an X.
Right. And I expect in the data path and to the controller, you don't have a you don't have the read as 0 except for the write back if it is needed. So make every time just keep read as 1, except for the write back when you are actually writing back into the memory, where the rest of the data path is unaffected on that side.
So we don't have to actually fix it to be high Z.
No, if it is, so you are not fixing it to the high Z. What you are sending out when read it 0?
Oh, yeah. In that case, it becomes an X because the mux uses like it goes through a mux, and the mux has gates, and she put like a Z into a gate.
Okay.
That comes out like as an X.
Yeah,
because,
in that
because of,
case, what you can, if you are uncomfortable with that part, it's basically an unknown, probably an unknown logic will come out of that mask at that point if read is 0. And what I'm saying, that should not affect your overall processor functionality, because read will be 0 only at write back stage. That stage, whatever you are reading out, it doesn't matter in the simulation. However, if you want to fix it, one way to do that, instead of, I would say, on the read, you can have one output register, okay, as a driving out from the register file, which will load upon the read signal or for that specific data from the address. You can do that way as well. Does that make sense, Evren?
yeah.
Yeah, so what I'm saying, that high Z and then unknown logic out of the mask during the write back phase, don't worry about that. It should not affect your like final outcome of the processor. Only catch is there during every other cycle. All the other 4 cycle, keep it read mode.
I think for his question, the reason why it's X instead of Z is because, like, if you do the register file test bench in there at the beginning, there's not really like one of the, like, the right address wasn't set to anything. So I think, like, when, I'm not sure about this, but I think when you have the register file and you don't put in all of the inputs in there, like you, like at the beginning of your initial block, you don't put any inputs for the right address, then the output will be high Z, will not be high Z, it will be X, because you don't know what the right address is, and it's a combinatorial circuit. So if you don't know one of the inputs, then you don't really know the, like, the outputs can't really know.
Oh, okay. I got it.
I think that's what he was saying.
Yeah. So if that is the case, then you are right also, like as you explained. If it is in the initial block and we are not setting up anything on the right address port, then its decoder and everything will be on the unknown logic. Okay.
Could we implement a workaround to this issue with like assign statements and make it a mixed implementation model?
I won't suggest that. Because like as a registered file in a standalone, when you are testing, this problem is coming up because the input is not set correctly. But in a real world, there will be some logic around that won't be high Z or anything, right? So when you plug that in the data path at that point, it should give you some value there, either all 0, all 1 over whatever, right? And then your unknown logic problem will be gone.
I see. Well, I was asking because I already implemented it that way, and I'm wondering if I should remove that now to make it a purely gate level implementation.
I think I would suggest that.
Okay. All right. Thank you.
Anything else from anyone?
Was anyone else going to say anything?
You go first.
Oh, okay. So for the report, so I didn't really get to like creating all of the control words for the module 7. So like I didn't create any of the control words. So for the implementation and design section, what would I put there? Like I know the general format, like the control unit sends the control word to the data path, and the data path sends like a 0 signal back to the control unit for the BNE and BEQ instructions and all of that. But I didn't really include any like explanation.
Yeah, so you can still discuss the design of it, And also mention that implementation specific was not done because of the time limitation and everything. That's okay. But at
Okay.
least you should discuss the design of it, whatever design has in your mind.
Okay. And do you think like any points will be deducted if it's discussed?
I don't think so. I don't think so.
Okay.
It's all about like design and implementation. As long as you are discussing your design, your not implementation will be like reflected on the testing part, and testing part is also basically I look for whatever you have done, not really some fixed story about like what you did. But even if you are done only till ALU or something, include that testing, and that should not be cause of any deduction if you have written it correctly.
Okay. So since I haven't implemented like the control unit part, like the system testing, then like so should I like not include the testing of the control unit? I mean the whole system, like putting in the file with all of the machine code and getting and receiving a file and receiving like the outputs of the machine code. Like, am I going to test for that or no?
It's up to you, like whatever you want us to evaluate. If it is partial, like something incomplete work, I would encourage you to submit that. Why not?
So like I didn't implement any of the control words, so there's no way like the testing would pass.
Right. So in your test report testing, I would expect there is no discussion about testing, the system level testing and all this stuff. You only discuss about what testing you did for the rest of the component.
Okay, so for that testing part, I wouldn't really include I would just include the parts that I actually did and
Right.
tested.
Right.
Okay, I think that's a lot because like there are like 27 units to like 27 units to test.
Right.
Like
right.
all those. Okay, so I just don't include that part. Or and the requirements, can we like since the requirements are almost the same, like I think the requirements are like the instruction, like explaining what the instruction set is. So can we keep that the same as our last project, or do we have to change it?
It is little bit fundamentally different requirement that here it's the same instruction set, that part will remain same, but it is more like an get level implementation. That is a basic fundamental requirement here.
Okay.
Get level, and for that, what are the different things we need to implement and so on and so forth.
Okay, so I should include in there like we have to do gate level implementation and we have to implement all of these components in order to create our.
Yeah, I would imagine introduction requirement section would be somewhat similar to your project to report, but not a copy paste from each other.
Okay.
It can be part is copied because they are same, but fundamentally they are targeted to different exercises, behavior versus get level. That's what you need to emphasize on that.
Okay. All right. Thank you.
Sorry, could you elaborate on that point a bit more? I'm a bit confused how I would differ my explanation of the architecture because that's separate from the implementation. Regardless if I'm using behavioral or a gate level implementation, shouldn't the computer architecture remain the same? What would I change?
Yeah, so basically your behavior level, remember it has these very simplistic components like one ALU and then one register file on this. But now at the gate level, each of them are now flown up with all this nitty-gritty detail lower level component, and those should be included in your requirement sections. Part of the introduction sections should reflect that as well, and same as the design and implementation sections.
I see. Yes, I did explain all those intricacies in the design and implementation section, so I should summarize that in the introduction?
Yeah.
I see. All right, thank you.
Okay, anything else from anyone? Remember this Wednesday, no class. So you're done with project 3 tonight. Enjoy your break, and we'll be back on Monday. And
Hey, Professor?
The final exam on Monday. Yeah, friend.
That's one quick question.
Sure.
I referred, like, this probably doesn't matter at all. I just want to make sure because the project matters. The project is a lot of points. I called it a mixed model instead of a behavior model a bunch, and I specified what that meant and stuff. But because some bits are behavioral still.
Yeah, especially the control unit. In that sense, it's kind of a mixed model. Yeah.
Got it. Okay. I just want to make sure that
But
was cool.
like mixed model is truly mixed model is one module, like let's say ALU, for example. Some part is described as behavior, some part using the get. That is a truly mixed model. Here, more like I would say system level, it is a mixed model because data path is in get level model and control is in behavior level model. That's why we can call it at the very top system level as a mixed model.
Because the memory too, right, would also be behavioral.
Yeah, memory is also behavior model. Yes.
Got it. Okay, thank you, Professor.
Okay, all right. Then remember, Wednesday, no class. Enjoy your break, and we'll be back on coming Monday.